So I guess we required Ravi's presence on the stage here to make it to work. Yeah. Okay, all right, so we are back in business. There's a slight change in title here. So I'll be talking about towards knowledge-aware AI, and first of all, thanks to the organizers and Ravi and others for having me here. So before I proceed further, I will just do some advertisement of my employer. So I'm from University of Science, and we have a strong AI group with 30+ faculty working on AI and related areas. So if you're interested, you can learn more about our research and people working there in this URL, ai.iisc.ac.in. And from this year, we are also starting a master's program dedicated on AI. So now moving on to the main part of the talk. So the overall thesis of our research is that background knowledge is really key to intelligent decision making. And our goal is, since this is like a web science workshop, so how we can kind of move towards more knowledge-aware AI, but the knowledge we would like to capture is from large unstructured data rather than hand coding it ourselves. And we see for many of the things that I'm going to talk about, web as that source of unstructured data from which we would like to harness knowledge and then utilize that to improve AI, right? So this is very much influenced by the same motivations about semantic web, but it's just that the methods that we are utilizing to get there might be a little bit different and more automated. So that's kind of like our background thesis, is that background knowledge is really key to intelligent decision making. And that's influenced by the fact that we as human learners, we make lots of decisions, intelligent decisions throughout the course of our day. And in order to make those decisions well, we utilize our knowledge about the world that we have accumulated over our lifespan. And that started right in the womb, and it's going to continue till we die, right? So our quest is how we can gather this kind of knowledge by interacting with the world over not just minutes and hours as it's done in current machine learning systems, but over years and decades, and do learning in a much more richer environment. So to make it, drive home this point through a concrete example, let's say I don't have time to go through lots of news sources every morning, and I want a system that will summarize the news for me, right? And such a system came across a sentence like State Farm stocks tumble along with Berkshire Hathaway. Now, in order to make sense of this particular sentence, what is being said here, we need to know that there is a concept called company, two of whose instances are mentioned here. State Farm is one and Berkshire Hathaway is another. There is something called a stock market where these company stocks are traded, and there is price associated with them, and there is volatility with those prices, right? None of those additional knowledge that's really necessary to make sense of this particular sentence is mentioned in the sentence itself, and that's by design of language, right? Because we use language for communication, and we want it to be efficient and interesting and informative, right? Because to convey this particular idea, if I had to start from what is a company, what is a stock market, it would require tremendous amounts of background context setting, which is of course going to be highly inefficient, and also maybe very much boring because you may know a lot of it already, right? So in order to analyze data, in particular language data, we have to swap in a lot of that external knowledge that we have built up over our lifespan. So now, even if you have all of that context knowledge, why there might be a correlation between the stock prices of these two companies, that's not immediately clear, right? But if I showed you some background knowledge and structure like this, which says that Berkshire Hathaway is mentioned in this particular sentence, they have a subsidiary called Heinz, which is insured by State Farm, and State Farm is also mentioned in this particular sentence. One of the plausible reasoning why there might be a correlation between the stock prices of these two companies is that something bad happened to Berkshire, and that's because of its subsidiary Heinz, and the losses of Heinz are going to pass on to its insurance company, so their prospects also don't look very good, and the market is factoring in that piece of information into its stock prices, right? So our analysis and interpretation of this particular data is probably much deeper now, compared to, say, 30 seconds before, when we didn't have this background knowledge to augment our and analyze our interpretation of this particular sentence, right? So this is a fragment of a much bigger graph, is what we call as the knowledge graph, where the nodes are objects of interest and the typed edges are the relationships connecting these entities, right? So our research goal is how we can build these kind of knowledge graphs at scale and make it available to intelligent AI and ML agents. And the thesis is that if you're able to do that, then their performance is going to improve significantly. So, so yeah, this is what knowledge graphs are, and Professor Hall also mentioned in her talk earlier on. So the need for knowledge in AI is long understood, right? Long realized. There have been lots of efforts for that also. But a big trust in the area came along when Google started using knowledge graphs to improve their web search. And one of the phrases they popularized was things and not strings, right? So previously, when you type in something in your favorite web search engine, your keyword was a string, your document was a string, and there was some glorified matching happening between those strings. But right now, the goal is to understand your intent, the entities, the relationships, the semantic nature of the information that you're looking for at a deeper semantic level. Also understand the content, the document collection at a deeper semantic level, and do this matching in the thing space, right? So we already are beneficiaries of knowledge graphs in our day-to-day lives. Whenever you search something on Google or Bing, you'd have seen this kind of panel on the right-hand side, right? So I search for Accenture, so I get a quick summary of a lot of information about Accenture, who is their CEO, what is their revenue, what is their stock symbol, and all of that. So that improves my web search experience, because now I don't need to go and read their Wikipedia page or 10 other pages to get the same amount of information, right? Similarly, another use case for knowledge graphs in the conversational AI, Bidisha covered that in great length in her talk. So right now we have, we want to talk with our computers and phones, and we already have these kind of deployed solutions in the form of Siri, Alexa, Google Home and all. But these are, again, good for question answering, right? So going back to the question after the previous talk, but they don't really lead to a discussion, right? So when you would ask the same question. For example, if I ask what is today's weather to one of these engines or one of these assistants, they will say what today's weather is, right? But if it knows that I'm flying out to Bangalore later tonight, and when I reach there it's going to rain, so it should also say hey, why don't you pack up an umbrella on your way out, right? So if it has that kind of a shared context, if it is able to analyze, then it could lead to a much more engaging discussion. And we feel that knowledge graphs, again, can provide a shared context to make these kind of dialogues more meaningful. So there are lots of other realizing these kind of benefits. There is significant amount of work around using knowledge, building knowledge graphs, and utilizing them for various applications. So I already touched upon the web search use cases, but Amazon over the last 2 years have also been building knowledge graphs called the product knowledge graph to improve their e-commerce operations, recommendations, and all. I also formed a company, Kinome, to help basically bring these benefits of knowledge graphs to enterprises at large. So here are some overview about different approaches towards building knowledge graphs. As I mentioned earlier, from around 1980s, there was this earlier effort called Psych knowledge graph. Then there was Freebase, which Google acquired, and then subsequently most of their knowledge graph efforts is centered around there. So those I would put in the high supervision regime, because those are primarily user contributed and crowdsourced solutions. There are something in between, like the Yago knowledge graph, which is starting from semi-structured data, like the Wikipedia info boxes and the category information, and trying to organize that data better. Then on the low supervision side of things, there are efforts like NEL and Deep Dive at Stanford, which is starting from purely unstructured data, so documents that are written in natural language, but at the end of the day, still trying to arrive at the knowledge graph, just like in those other efforts. Right? Before joining IISc, I was a postdoc in the machine learning department at CMU, and we were part of this project called NEL, which stands for Never Ending Language Learning. So that's kind of like that low supervision setting that I was mentioning earlier. So where NEL's goal is to read web documents on a continuous basis and build these kind of knowledge graphs at scale. So it's one of its kind, a unique system, which has been running for more than 9 years now, and has built up a knowledge graph with 100 million plus edges, a fraction of which actually is what you see here, right? So this is actually a true fragment of that knowledge graph that NEL has built, where it is able to surface interesting information, knowledge like Toronto Maple Leafs, their hometown is Toronto, they play hockey, they won Stanley Cup and things like that. So if you're interested, you can go and visit this URL, rtw.ml.cmu.edu, where RTW stands for read the web. So that's kind of like the scope of the project. So I'm not going to talk about how NEL works and all of that, so because that's a talk in itself. But you can read about our lessons learned and opportunities and problems that we see in this particular area in our communications of the ACM paper from May last year. So, and we continue to do this line of research in our group at IISc. So what I'm going to do next in the second half of my talk is give some glimpses of some recent research in this particular area. I don't expect you to know all about kind of like the methods, but this is just to give you a flavor. So, I'll be kind of like thinking about two types of knowledge. I mean, knowledge representation is kind of like our core focus. So one is the graph-centric view, knowledge graphs through entities and relationships. So that's what I've been motivating so far. But with advances in representation learning algorithm, deep learning algorithm, we now have dense representations of knowledge, where the entities in this graph now become points in some high-dimensional space. So with each node, you have basically a vector that's connected with it, right? So these are just kind of like two types of representing the same knowledge, and they have their own pluses and minuses, right? So while inference in these dense representations tends to be better, more accurate, gives you better performance, but they are to a large extent black box for us, because these dense representations learned by deep methods are not really interpretable for human consumption as yet, right? While inference over these kind of graphs tend to be much more interpretable, because you can get paths of chains of reasoning, which is good for human consumption. So we kind of think of this as a spectrum of two ends of the line, and rather than choosing one or the other, we are interested in how we can go back and forth between these two types of representation. And some of the things that I'm going to talk about is going to have this kind of a flavor. So the first problem that I want to talk about is the problem of canonicalization. So this is joint work with my PhD student Shikhar, and which came out in the web conference last year. So the canonicalization problem is given these kind of noun phrases, Barack Obama, Mr. Obama, George Bush, Mumbai, Bombay, Madrid, how do you figure out that Barack Obama and Mr. Obama is actually the same entity? Similarly, Mumbai and Bombay are again the same entity, but George Bush and Madrid are different entities on their own. So this is a pervasive problem, because anytime you have a situation where multiple sources are generating data without any agreement on the terminologies, so they are just going to use whatever references they want to refer to those entities. Now it's your job to basically merge those different mentions and do the normalization and the canonicalization. So for this, we have a system called CESI, which stands for canonicalization using embeddings and side information. So at a very high level, given unstructured document, we find these entity relationship or noun phrase relationship, noun phrase, subject, verb, object kind of triples from the unstructured data using these what are called these open information extraction techniques. Build a knowledge graph involving those noun phrases and relation phrases. And then using these graph embedding techniques over the last few years, there have been explosion of methods which given a multi-relational graph that we construct here, that's going to give you embeddings for the nodes and the edges of that graph in some vector space. So that's exactly what we do. And then finally, we do some sort of clustering of those noun phrases to discover the canonicalized entities. So rather than doing this kind of like the straightforward approach, we add one more twist here, which is to incorporate any type of side information that you may have access to say that, okay, these two noun phrases are actually like, referring to the same entity, because you may have some expert inputs available or some off-the-shelf tool which is able to solve this problem at least partially. So what we do is we take judgments from those kind of side information and then utilize those side information to influence these representations that we are learning for the graphs. Right? And we find that if you utilize those kind of side information, that's actually is a helpful thing. And in a lot of our work, you'll actually see this interaction between having a principal optimization, but also influencing that with available side information, because we think that's a valuable source and we should not let it go. So without going into the details of the method, I just want to show you some highlights of embeddings and canonicalized clusters we are able to learn. So by going through that CESI method, for each one of those noun phrases and relation phrases, we find an embedding in a high-dimensional space, and that I'm projecting that in a two-dimensional space here for better readability. And the model's way of saying things is like, if multiple noun phrases are co-projected in the same part of the space, then they are canonicalized versions of each other. So we already see interesting patterns, like it's able to discover that GlaxoSmithKline and GSK are actually referring to that same entity. So that's interesting, because on the surface, both of these two strings and noun phrases actually look very different, right? So if you try to do edit distance between these two noun phrases, that will look very different to each other. But because we are utilizing the structure, right, so how these noun phrases are related to other noun phrases and learning embeddings based on that, we are able to bring those closer together. Similarly, before this CESI output, I didn't know that Sakyamuni is actually another name of Gautam Buddha. How many of you knew that before? Okay, like 4 people here, right? So you're already learning something new. Right? So in addition to this noun phrase canonicalization, we can also do relation phrase canonicalization to say that declare war against and have declare war on actually are kind of roughly the same relation. So the source code of this is available in case this problem is of interest to you. Now moving on, so we live in a dynamic world where the world is changing, new knowledge is constantly becoming available, and even though I mentioned that there have been plethora of work in learning embeddings of these knowledge graphs, but most of those work have ignored the time aspect, right? So in this particular work, we address the problem of ignoring time completely, how we can represent time as a first-class object in the learned representations, right? So because, say, in your knowledge graph, you may have a fact saying that Barack Obama or Bill Clinton was president from 1993 to 2001, right? So if you have those kind of time scope facts, how do you utilize that time and represent the time also in your representation to learn the embeddings? So we have a system for that called HYT, which stands for hyperplane-based temporal embedding, where for each time interval, we actually have a hyperplane, and then we project these facts onto that hyperplane and do some scoring to learn the embeddings while in a temporally aware manner. So again, I don't have time to go into the details of that, but the point here is that time is important, and it turns out that if you are actually learning these temporally aware representations and then doing inference, right, utilizing those temporally aware representations, turns out you can do better inference and predictions compared to representations which are temporally ignorant or ignore time completely, right? So here are, through a variety of benchmark data sets and tasks, we are able to show improvements in performance. Moving on, the next work I want to talk about is how we can do relation extraction or using side information. So this is kind of like another way to look at this work is, so we talk a lot about deep learning methods nowadays, and those methods have been very successful when you have tremendous amounts of training data, right? So gold training data, which is humanly annotated, and millions and thousands of them are available, but not all tasks are equally fortunate to have that much of labeled training data, right? So here we are interested in how we can move the needle and then utilize or adopt those kind of deep learning methods in what are these like noisily created training data or what is called is the silver training data, because silver is cheaper than gold, right? So here we are interested, like Obama was elected as the president of USA yesterday. We want to extract that president of relationship is true between the Obama entity and the USA entity. So this will be one edge in my graph, right? So given the political realities in US, some people feel comfort in seeing these kind of examples, given what is going on today. So I haven't updated the slides. If people get at least one thing, maybe this is it from my talk. Yeah, that's right. Yes, we can take a leaf from, I guess, the current president's book. Okay, so one, of course, approach is that you can have like a highly supervised methods to go and label sentences with these kind of information. But as we all know, that's not going to scale. So we're interested in how we can train these kind of extractions from a distantly supervised setting. So here, rather than having label instances at a sentence level, what we do is we have actually label at the tuple level or seed level. So given a particular relation, say Prime Minister of, we are going to give some seed examples like Narendra Modi is Prime Minister of India, right? So maybe 5 or 10 or 20 such tuples, because the assumption is it's easier to give these kind of seed information as supervision compared to giving label sentences, right? And doing labeling on that. So given these kind of seed tuples, we go out to our corpus, which could be the entire web, and then find instances where both of these two entities are present, right? So Narendra Modi and India is present in this particular sentence. Narendra Modi, Prime Minister of India, visited USA. You can also have sentences like Narendra Modi paid respects at Amar Jawan Jyoti on India's Independence Day, right? So there's a typo here, it should have been paid. So the point to note is not all sentences mentioning these two entities are going to always express the relationships that we care about, right? So here the relationship is Prime Minister of. So while it's expressed in the first sentence, that's not the case in case of the second sentence, right? So what we do is we create a bag of these sentences, which is called the instance set, and then we assign that label, the Prime Minister of, over this whole bag, right? So the point is that I have all of these sentences, and at least one of those sentences are expressing that relation among these two entities, right? So this now becomes a multi-instance learning problem as opposed to in standard machine learning, where for each instance you actually have a label, right? So rather than having label on each instance, now we have a label over a set of instances. So that's why the multi-instance learning. So the point is that this kind of data is easier to generate because we can automatically generate this type of training data, and it's going to have noise because we are automatically generating. So we utilize something called graph convolution networks, but in the interest of time, we will skip here. There's lots of work here as well in Ravi's group on doing GCNs. So we use GCNs and a deep model to train in this kind of distantly supervised noisy training setting. Of course, my goal is not to go through this whole architecture, but the point is to say that now we have tools to use deep learning methods, but over noisily created training data, which is in a distant supervision setting here, and we can do end-to-end training just like in the fully supervised setting. So utilizing these kind of methods, we are able to actually show improvement in performance, both in terms of precision and recall on multiple benchmark datasets. I'll skip here. If you're interested in GCNs, we also have recent work on incorporating confidence over those label predictions, and that's upcoming work in AI stats. So so far, whatever I've talked about is about how we can use text as a source to derive knowledge, and which then in turn could help improve AI and learning agents. But we as humans, it's not that we just read documents and shut our eyes and close our ears, right? So we gather evidence in a multimodal setting. We see things, we hear things, and we do some sort of multimodal fusion in our head to build up a model about the world, right? So in our more recent work, we have tried to go beyond text and start looking at images. So the current state in computer vision is that given an image like this, you are able to ask questions like how many people are there in this particular image, right? So state-of-the-art systems will say like there are 3 images. So that task is called VQA, which stands for Visual Question Answering, right? But that's not the only type of questions I would like to ask about this particular image, right? So I would like to ask things like, okay, I know this guy is Obama, this is Elizabeth Warren, but I don't know who this guy is, right? So I would like to ask questions like, who is that person standing to the left of Obama in this particular image, right? So in order to answer those types of questions, just the content of the image itself is not good enough, right? So we have to overlay that about the identities of these entities, about our knowledge about the world, and utilize that in context with the content of the image to answer those type of questions. And that's exactly where knowledge graph come in, right? So we want to incorporate our knowledge represented in the form of a knowledge graph, link it to the image content, and then try to answer these types of questions, right? So we are posing this as a task called knowledgeable VQA or KVQA, right? So if you have, if you're doing this kind of reasoning and analysis in the context of a knowledge graph, now you're able to ask questions like, okay, do all the people in this particular image have a shared profession, right? So if I'm able to link them to the respective nodes and then do reasoning over this graph, then we can say, yes, they are, this all converge on the politician node, so they are, they have a shared profession, right? So we are not just introducing a task, we have also created and released a new data set called KVQA that's available from this URL, which has about 24,000 images and 183,000 plus Q&A pairs of questions and answers. But all of them, in order to answer, you will actually have to do some sort of reasoning over a knowledge graph. So this is a work supported by Intel, among other funders. And we are really excited about this, right? That's kind of like our way of pushing and the state-of-the-art in computer vision by making them more knowledge aware. Since this is a web science gathering, and fake news is kind of like the hot topic nowadays, I just want to highlight that we also did some work earlier on source credibility, again posing that as an inference over some sort of like a graph. So with a paper in AAAI 2016, which looks at not only the sources, we also extract the evidences that are present in those sources and how they may support or not support particular claims. So we pose this as an semi-supervised learning inference over the graph, and then we saw some improvement compared to the state-of-the-art at that particular point of time. So we do a lot of work around knowledge graphs and how we could utilize them to improve decision making. So overall, our work spans the areas of machine learning, natural language processing, and large-scale data analysis. By extraction of structure and knowledge graphs out of them, we would like to improve decision making. There's a lot more to talk about, so if you're interested, you can go and visit this URL. So thanks again for your attention, and if you have any questions, I'll be happy to address them.
We can have a couple of very quick questions since we are running really short of time.